Okay, so we should, so what I'm going to be doing today is I'm going to start with a problem related to what we were doing on Friday, because I only got to do one problem associated with the Gaussian-Clapeyron equation. After that, we'll get into the material that I have listed on Blackboard to do, which is going to be the heating and cooling curves. And then if all goes well, we'll take a short, well, about 15-minute break, and then we'll come back and finish it up with phase diagrams. So that's how I normally run lab lectures, is we'll go for roughly an hour. Sometimes it's a little bit more, sometimes it's a little bit less. It depends upon how fast I can talk. We take a 15-minute break to just let everybody get up and move, and if they want to go get a drink or whatever, do so, and then we come back and finish. Okay. Any questions? Then we're going to go ahead and get started. So, if you recall our discussion on Friday, the last thing we were talking about are vapor pressure curves. And if you plot temperature versus pressure, you tend to get a curved line. You can perform mathematical functions on this line, such as taking the natural log, essentially. And what we can obtain is a linear line, which in chemistry we like to have. That line that results gives us the equation of natural log of P2 over P1 is equal to negative delta H of vaporization over R times 1 over T2 minus 1 over T1, which is known as the Clausius-Clapeyron equation. So let's look at a problem associated with Clausius-Clapeyron equation. The delta H of vaporization for hexane is 28.9 kilojoules per mole. The normal boiling point of hexane is 68.73 degrees Celsius. What is the vapor pressure? Of hexane at 25 degrees Celsius. Okay. So let's peel out the information that is given to us in this problem. First of all, we have the delta H of vaporization as being equal to 28.9 kilojoules per mole. The next thing I notice is I have this term normal, and that's something that we haven't discussed yet, and that is normal when we're talking about normal boiling point, normal melting point, and when we get into the phase diagram, what it means is that this occurs at 1 atmosphere. So we know our first pressure, that is going to be 1 atmosphere. Our first boiling point is 68.73 degrees Celsius. And we have been asked to determine the second vapor pressure when the temperature is 25.00 degrees Celsius. Now, looking at this, because I have a change in pressure and I have a change in temperature, that is indication that the Clausius-Clapeyron equation is going to be used. And so we need the ideal gas constant in energy, which is 8.314 joules per mole Kelvin. Now, if you'll recall, when we were discussing the ideal gas constants or constants in general, constants I kind of think of as dictators because they are going to dictate the exact unit everybody needs to be in. So our unit of energy needs to be in joules. So the first thing I'm going to do is I'm going to convert this delta H of vaporization from kilojoules into joules per mole. The second thing is that the temperature needs to be in Kelvin. So we're going to need to convert both of these temperatures into Kelvin. So the temperature 1 is actually 341.88 Kelvin. And temperature 2 is going to be 298.15 Kelvin. By taking the time to write all of your variables down and making sure all of the units match, it makes the calculation simplified because we're not having to worry about changing the units as we go. They're already there. So this equation becomes, again, the Clausius-Clapeyron equation is the natural log of P2 over P1 is equal to the negative delta H of vaporization over R times 1 over T2 minus 1 over T1. So plugging in what we know, we have the natural log of P2 over 1 atmosphere is equal to the negative of 28,900 joules per mole divided by 8.314 joules per mole Kelvin times 1 over T2, which is 298.15 Kelvin minus 1 over T1, which is 341.88 Kelvin. So clearing out the right-hand side of this equation, natural log of P2 over 1 atmosphere is equal to a negative 1.4913. Now, to get rid of the log, we have to take the opposite. And if you have always been confused about what the opposite is, you can actually look at your calculator, find the natural log button, and what's above it is its opposite. So in this case, we're going to take the E of the natural log of P2 over 1 atmosphere is equal to the E of a negative 1.4913. Taking the exponential of a natural log makes that go away. So the right-hand side, the left-hand side becomes P2 over 1 atmosphere. And the right-hand side is equal to 0.225. Now that makes it a much easier problem. So P2 multiplying both sides through by 1 atmosphere gives you a P2 of 0.225 atmospheres. Questions?
Yes.
How important are siblings in your financing?
Okay, I'm glad somebody finally asked me that question. I actually don't worry about sig figs in anything but the laboratory. So in class, now I should say active worries about sig figs too. But on a test, you're not going to have to focus on significant digits. I want to make sure you can know what you're doing more than worry about significant digits. So in the laboratory, you will have to worry about significant digits, and in active, you will have to worry about significant digits. But the rest of the time, you will not. Okay, so hopefully that now gives you two examples that you can perform the Clausius-Clapeyron equation based off of to give you something to look over and help you along the way as you're learning to do the Clausius-Clapeyron. Now what we're going to get into is we're going to get into heating and cooling curves. I am going to start by drawing a heating and cooling curve. Then we're going to discuss what each line segment of the heating and cooling curve means. So if I'm dealing with the heating curve, heating means the temperature increases. So if we're looking at temperature as our y-axis, with a heating and cooling curve, the temperature is going to increase. We're then going to hit a flat line. It's going to increase again, hit another flat line, and then we'll increase a fifth time. If I'm talking about a cooling curve, it means that the temperature is decreasing. So it would wind up being the opposite. Okay. The first thing is that we need to describe is what these lines are associated with. These lines that are parallel to the x-axis. One of them is the melting point of the substance. The other one is the boiling point for that substance. It is true no matter whether we're talking about a heating curve or a cooling curve. So if we're talking about water, it would be 0 and 100 degrees Celsius. If you're talking about something else, I will give you the melting point and boiling point of that substance. Now, we're going to talk about each line segment in the process.
Okay, segment 1. As I've drawn it on the heating and the cooling curve, represents a solid.
Now, basically what you can think about is, yes, a solid can increase temperature without melting. We can have snow outside at -32 degrees Celsius, and it's still going to be the same hard snow at -5 degrees Celsius, even if it increased. You're still gonna have snow. So you can, in the case of water, you're still going to have the solid in the form of ice.
Segment 2. With segment 2, you have the solid and liquid in equilibrium with one another.
So what happens is the solid molecules absorb enough energy that it starts to overcome the intermolecular forces, allowing that solid to transform into a liquid. But the liquid molecules, as they're moving around and bouncing off of one another, they lose energy. And so they wind up depositing right back on the solid. So this process is at equilibrium between the two. So I guess instead of a double-headed arrow, if I'm going to, since we're going to get into it eventually, and it all depends upon whether I have to use a program or whether I'm drawing it. Another way to do it is this type of arrow notation, which is equilibrium notation. Now this process goes back and forth until enough energy has been obtained to get all of the molecules to transfer from the solid into the liquid form. And the amount of energy needed to accomplish that is called the delta H of fusion. Which is also equal to the negative delta H of freezing. They're the same value, same numerical value, but opposite in sign. So what that means is over here on the heating diagram, it's going to be a positive delta H of fusion. Because you have to add energy in order to break the intermolecular forces of the solid and convert it into a liquid. Whereas over here, where it is cooling off, we would wind up using the negative delta H of fusion because, and the reason we don't call it the negative delta H of freezing at that point, even though technically that's what it is because when you go look up these values, they only give the delta H of fusion. So although this is technically the delta H of freezing because you have a liquid freezing and depositing to form a solid, we don't call it that. We just use the negative delta H of fusion because they're the same value. They're just opposite in sign.
So let's move to stage 3. Stage 3 is where you have a liquid. And I mean, you're used to heating up a pot of liquid on a stove from 25 degrees Celsius until it starts to boil. But it's still liquid throughout that time frame. And then we get to stage 4, or line segment 4. At line segment 4, you have a liquid that is in equilibrium with the gas. So in this particular one, what's happening is you have these liquid molecules. They have gained energy. Some of the liquid has enough energy to pop off and form a gas. But those gas molecules, they bounce off of one another, they bounce off of the wall, they bounce off of other things. And when they collide with the wall or the other items, they lose some of that energy and reform the liquid. And this process goes on and on and on until we get enough energy in order to break all of the intermolecular forces. The amount of energy needed to break all the intermolecular forces is called the delta H of vaporization. The delta H of vaporization is the same as the negative of the delta H of condensation. Again, you're going to use the delta H of vaporization for both the heating curve and the cooling curve. The only difference will be what the sign will be, and that is based off of whether you are absorbing energy or giving off energy. Because one thing you need to remember, plus and minus do not mean the same thing in algebra that they do in chemistry. Plus means you're taking something in, minus means you're giving something off. So a plus means you're absorbing energy, whereas minus simply means you're giving off energy. Again, these are the same value. But simply opposite in sign. Now, one of the things that isn't, I mean, I tried to draw it that way, but it's not ideal, is that the delta H of vaporization is significantly larger than the delta H of fusion. Why is the delta H of vaporization significantly larger than the delta H of fusion?
You have to break all the attractive forces besides fusions just partially.
Yes. So delta H of vaporization is larger or significantly larger than the delta H of fusion because you have to break all intermolecular forces. And it's typically represented by a longer line. And that's why I said I tried to illustrate it, but I just looking up here, it doesn't look like I illustrated it that well. but I did try to illustrate it. And then section 5 of this is going to be the gas form. Any questions about heating and cooling curve from a conceptual standpoint? So if I gave you a heating and cooling curve, could you tell me what the freezing point of the substance is? Sure. It's that lowest line. Whatever it is attached to, that's the freezing point of the substance. The boiling point would be the upper line. Whatever its temperature is, that would be the boiling point of the substance. Now, while I want you to be able to interpret the graph, I also want you to be able to do some calculations with the graph. So I'll give you my process to perform calculations with heating and cooling curves. The first step is I go ahead and just scratch out a general heating and cooling curve. It doesn't take that long, and it does make a difference in helping you keep things straight in your head. The second thing I do is I label the melting point and boiling point with the value given. Now, I should say, let me put one little caveat on this. If it is a substance like benzene, acetone, isopropyl alcohol, diethyl ether, something that I don't expect you to know, the melting points and boiling points, I will give them to you. But if it is water, I expect you to know that. And therefore, you will not be given the melting point and boiling point of water. But otherwise, it will be given. The third thing I do is then I evaluate the problem to determine the temperatures or the temperature differences, the temperature of the transition. And make note of it on my graph. This step right here will keep you from it. These 3 steps will typically keep you from doing more than is necessary from a calculation standpoint. Then I actually start calculating. Segment 1, 3, and 5 on the graph, you will use Q is equal to MC delta T, which is the same equation that you used in college chemistry 1, where Q is equal to heat, M is the mass in grams, delta T is T final minus T initial. Typically, these are going to be in degrees Celsius. And then the C will vary. You will have C solid, so the specific heat of the solid. You will have C for the liquid. And you'll have C subscript G for the specific heat of the gas. Now, this may be a little bit different because at least in the laboratory for College Chem 1, when we had Q equals MCAT, we used the specific heat of the liquid because that was what we were working with, is the specific heat of water in liquid form. But you do have to understand that there is a specific heat for each state of matter. And that specific heat is related to how much energy must be added to start to eliminate intermolecular forces. Now, for step 2 and 4, your heat is going to be equal to N delta H, where N is going to be equal to the moles of the substance. And that is because your enthalpy is going to be in moles. Now, with this particular step, you do have to pay attention. This is where you have to pay attention to whether you've got a heating curve where the delta H is going to be a positive, or a cooling curve where the delta H is negative. You only have to worry about it on this particular step, remembering these signs. Because if you do T final minus T initial in step 1, 3, and 5, it'll automatically tell you whether it's positive or negative. It will give you the correct value. But in step 2 and 4, you have to remember, are you dealing with heating or are you dealing with cooling? So you know what sign the enthalpy should have. Step 5 is typically to add up the Q values together. To get the total heat required. Or released. So let's look at an example. How much energy in kilojoules is required to melt 220.1 grams of ice at negative 25.67 degrees Celsius and bring the resulting liquid water up to 75.00 degrees Celsius. Okay. Step one, heating or cooling curve? Heating, because I'm melting. I'm requiring energy. So I'm going to draw my heating curve. Step two. This is ice and water. So what are my melting points and boiling points?
Where's your melting point? And I'll get your boiling point.
Step three, evaluate the problem to determine the temperature of the transition and make note of it on the graph. I'm wanting to go from a negative 25.67 to 75. This does not have to be exact, folks. This is just there to help us. So in other words, we are going from 25 up to 75. And we are traveling in a positive direction. Now, before we can start the calculation, the other pieces of information, and this information would be given to you, but other things that you're going to need to know. The specific heat of the gas is 1.84 joules per gram degrees Celsius. The specific heat of liquid is 4.184 joules per gram degrees Celsius. The specific heat of the solid is 2.09 joules per gram degrees Celsius. The delta H of vaporization is equal to 40.7 kilojoules per mole. The delta H of fusion is equal to 6.01 kilojoules per mole. Now, if we go back to my labeling, we are in section 1, 2, and 3 but we don't need segment 4 and 5. So we're gonna have 3 major calculations here. The first calculation is Q equals MCAT, but specifically it's going to be for the solid. So our Q is equal to the mass, which was 220.1 grams, times the specific heat of the solid, which is 2.09 joules per gram degree Celsius, times the change in temperature. It's always T final minus T initial. And for this segment only, what is the final temperature? 0. So it would be 0 degrees Celsius minus a negative 25.67 degrees Celsius. So the heat just for section 1 is 11,808 joules, or 11.81 kilojoules. Segment 2. Our Q is equal to N times delta H, in this case, delta H of fusion. Before we can get to this, we need the moles. So we're going to convert our grams of water into moles of water using the molar mass of water. And that comes out to be 12.23 moles of water. So the specific heat is equal to 12.23 moles times our delta H of fusion, which is 6.01 kilojoules per mole, for a heat of 73.5023 kilojoules. Segment 3. Again, we're using Q is equal to MCAT, but this time we're in the liquid phase. And so it's the specific heat of the liquid times the change in temperature. So Q is equal to 220.1 grams times the specific heat of the liquid, which is 4.184 joules per gram degree Celsius, times T final. What is the final temperature of this particular segment? 75, because that's where we're stopping at. And what was the initial temperature of that segment? 0, because that's where that segment started. So Q is equal to 69,067 joules, or 69.07 kilojoules. So to answer the question, we need the total heat required. So we're going to add these together. So we're going to add the 11.81 kilojoules plus 73.5023 kilojoules plus 69.07 kilojoules. So our total heat is equal to 154.4 kilojoules. Okay, I know people were mainly focused on writing down what I did and what I said. So now I want you to take a moment to look over it and make sure you understand it. And ask questions if you have questions. Yes.
What does the C stand for?
C is specific heat.
I'm assuming this big heat's gonna be given on like an exam, right?
You will be given the specific heat. You will be given the delta H of vaporization and delta H of fusion. If it is some compound besides water, you will be given the melting point and boiling point. And if I don't give you the formula of a compound, I will also give you the molar mass. In fact, normally I give the molar mass because you've only got so much time on my test and it adds up quick when you start doing something of this nature.
I used to hate having to like stare at the periodic table across the class and try to like.
Well,
search it.
You will always be given a periodic table as the last and formula sheet as the last page of my test. So you won't have to stare across the classroom.
You're wonderful for that.
So what will be on the formula sheet? Q equals MCAT. I'm not going to specify the specific heat, just Q equals MCAT. And Q is equal to N times delta H. And you will be given the Clausius-Clapeyron equation, since those are the three we've talked about, I believe.
Just so I don't have to know the specific heats for like water.
No.
Just the boiling and melting
Just the
point?
boiling and melting point.
Okay.
Something you should have known since pretty close to being a child.
Yeah, yeah. I was just making.
I'm not going to make you know something that I give a lot of stuff.
I was gonna say that's a lot of numbers, but I'll get there. Like, we'll figure it out, but.
Okay. Did anybody catch the similarity in the equation? When do you use Q equals MCAT? Whenever you're switching temperatures. So whenever you're going up or whenever you're coming down, you're going to use Q equals MCAT. So you don't have to, what I'm trying to say is it's not necessary to memorize 1, 2, and 3 as Q equals MCAT. If you understand, now think about, and why is that? Think about what the formula says.
It has to change in temperature.
It has to have a change in temperature. And those are the sections that have a change in temperature. The section that doesn't have the change in temperature doesn't have a change in temperature part of the equation. So again, I'm trying to give you some little clues to use. Any questions about heating and cooling curves? Because some of the same stuff I've been talking about is the same stuff I'm about to talk about, but in a different format. Yes.
So when would you use the delta H like vaporization?
So delta H of vaporization is used if you cross this line. So if I stop at 100 degrees, I would use the delta H of vaporization. If I stopped at 0, I would still just use the delta H of fusion.
So
As long as I'm converting it from a solid, as long as I'm converting this from a solid to a liquid, even at 0 degrees, it's just the delta H infusion.
So would you do it on the flat part right under 100 degrees Celsius, or?
Well, it's supposed to be that line was supposed to be at the 100.
Okay.
I have spatial issues sometimes drawing.
So then if section 3 did go all the way to 100.
It all depends, okay, the question is, if section 3 went all the way to 100, would you use the delta H vaporization? It all comes down to how it is worded in the question. Did I convert it to a gas at 100 degrees? If I converted this, if instead of stopping here, I said you're converting it to a gas at 100 degrees, then yes, you would have to use the delta H of vaporization. But if I just said you're converting it to a liquid at 100 degrees, then you would not use the delta H of vaporization, because the delta H of vaporization is when you're going from that liquid into the gas phase. Does that answer your question?
Yes.
Make sense? So you got to look at how it's worded. Wording is very, very important. And I try to watch my wording so that I convey exactly what I am trying to intend. Okay. What time is it? Well, so that what I want to do at this point is I want to give you a 15-minute break. So it is 3:30, so 3:35 plus 15. So 3:40, 3:50 is when we'll come back here. Okay, so what we're about to discuss, it really has a lot of similarities between the heating and cooling curve. But so let's talk about how they differ. So we've talked about a heating and cooling curve. And with the heating and cooling curve, we had temperature on the y-axis. And we had basically let's call it reaction progress. On the x-axis. With respect to the heating and cooling curve, we are definitely going to be performing calculations on the exam. Now, does that mean you don't have to understand what's going on? No. I expect you to understand what each segment indicates as far as the state of matter at that point. But you don't have to, you won't go into as much detail on understanding as I went into the initial piece. I wanted you to understand what everything meant before we did the calculation. What we're about to do is we're about to do the phase diagram. When we talk about a phase diagram, the pressure is going to be listed on the y-axis. And the temperature is on the x-axis. For purposes of the exam, the phase diagram will be conceptual questions. As well as, and basically with those conceptual questions, it will require interpretation. Of the graph. So that is the difference. They both give us a lot of the same information. They both talk about states of matter, whether something is in solid form or liquid form or gas form, or whether it's transitioning from a solid to a liquid or transitioning from a liquid to a gas, stuff like that. They both give some of that same information. But from a test perspective, we will use them differently. So let's talk about a phase diagram. I'm going to start with a very general phase diagram, and then I'll draw one that's more precise. So again, you're going to have pressure on your y-axis. You're going to have temperature on your x-axis. In other words, we really have two variables. What is our state of matter now from both a pressure and a temperature perspective? Whereas the heating and cooling curve was really just what is the state of matter from a temperature perspective. Now we're dealing with both pressure and temperature. I didn't want that. What are you doing to me? Okay. Now, phase diagrams can actually get a lot more complicated. And if you do the research involved in phase diagrams, then I'll let it get more complicated, but I want to get a basic understanding of the phase diagram. Because that will do for our purposes in college chemistry too. With this phase diagram, there are three parts. Everything to the left of the first line is a solid. Everything that occurs between the two lines is in liquid phase. And everything that is to the right of that second line or the outer line is in gas phase. Now, in phase diagrams, there is a point where all three phases exist. And this is called the triple point. You have to have just the right pressure and just the right temperature for you to have a triple point so that you have solid, liquid, and gas all existing simultaneously. Now, at this liquid gas line, up at the very, very top, where you're at high pressure and high temperature, you can get a supercritical fluid. Now, a supercritical fluid exists when you have such high temperatures that the liquid is going into gas phase, but such high pressures that the gas is going into liquid phase to the point you cannot tell the difference. You can't tell whether you have a liquid or if you have a gas. That's what a supercritical fluid is it's the gas molecules are so close together, they almost look like a liquid. And the liquid molecules are so far apart, they almost look like a gas.
So it's steam used in the food, or is that like too much liquid?
No, steam has gone straight into the gas phase where all the molecules are far apart. A supercritical fluid, like I said, is high temperature and high pressure. And at that point, it's the molecules are just far enough apart, they look like a gas, but close enough together, they look like a liquid. In the flipped classroom lectures, when you get to phase diagram, there was the title is underlined because it's a link. And there's actually a really good video. So you can truly picture what these states of matter look alike at the various points.
What's an example of that supercritical fluid?
I mean, water can be a supercritical fluid. It's not very likely because of the pressure that it has to be under. That's the key, is the entire key is high temperature and high pressure simultaneously, which you get something at a high enough temperature and a high enough pressure, and you've got something that can explode pretty easily. So it takes certain equipment to make it happen. But we have been able to make it happen. So, okay. Now, in our last example, when we were dealing with enthalpies of vaporization and enthalpies of fusion, they're on here too. The enthalpy of fusion is associated with that line because that is the location where a solid is converting into a liquid. And the enthalpy of vaporization is associated with this other line because that is where a liquid is converting into a gas. Now, in the previous example, when we were doing the heating and cooling curve, there was but one value. Why was it at one value when, I mean, this looks like it could be multiple values of temperature. So why was it at one value?
It wasn't pressure taken into consideration.
Pressure wasn't taken into consideration. So when we were doing the heating and cooling curves, I gave you just an enthalpy of vaporization and an enthalpy of fusion. That's because I wasn't telling, what I did not tell you is that was at normal pressure. So when we were doing the heating and cooling curves, that was at normal pressure, which is 1 atmosphere. Whereas this, you could actually change your temperatures, your melting points and boiling points at a different pressure, and you could still do the mathematics. So there is one, so we know that a solid into a liquid is evaporation. I'm sorry. No, it is melting. And a liquid into a solid is freezing. We know that a liquid into a gas is evaporation. And we know that a gas into a liquid is condensation. But there are two other types of phase changes that can occur. Yes.
I think I was gonna ask what would it be when a solid went to a gas, since there was that point where it was.
When a solid goes straight to a gas, it is called sublimation. And when a gas goes to a solid, it's called deposition, because the gas molecules deposit onto the solid. Which we didn't have that opportunity to discuss when we got into the heating and cooling curve. But you do have the opportunity to discuss sublimation and deposition when we're talking about the phase diagram. Okay. So it's going to take me a second to put the next thing together, because I'm going to illustrate the types of questions you can expect to see about phase diagrams. But now I've actually got to draw in temperatures and pressures. Okay. That's my rough drawing.
So one possible question. Let me give everybody a minute. Does everybody have it drawn that's trying to draw it? One possible question would be, what is the normal freezing point? What does normal mean? 1 ATM. First thing I do is I go ahead and I make note. This is the solid, this is the liquid, this is the gas. If I'm talking the freezing point, I'm talking the point where liquid becomes a solid. So I would trace it out to that point and then down and estimate. So roughly this one had a freezing point of 180. For the most part, because even mine line got off a little bit, I would have given you anything from 100 to 200. I realize that lines become slightly angled. I also realize that your opinion and my opinion are going to be potentially different. So I'm going to make sure that I give enough of a variation here to allow for those things. Because you're probably not going to have a straight edge on the test. So, another type of question that could be asked is, what state or states of matter exist at 1.25 atmospheres and 300 degrees Celsius? Okay, 1.25 atmospheres, 300 degrees Celsius. The only state that exists is a liquid. Another way that this question could be asked is, what is the temperature and pressure of a compound at the triple point? Well, this is the triple point, so that's, you have to estimate what that is.
And it's roughly 0.65 atmospheres and 100 degrees Celsius. Another possible question is, what phase change occurs at 400 degrees Celsius when the pressure drops from 1.4 atmospheres to 0.5 atmospheres. So 1.5 atmosphere, 1.4 atmospheres and 400 is roughly there to 0.5 atmospheres is roughly there. So yes, it evaporates. All of these are possibilities. This type of question are possibilities. It's, if you know the solid, liquid, gas, if you know the triple point, if you know where supercritical fluid exists, then it's mainly a matter of interpreting the graph. Questions for me? But again, phase diagram is a lot like the heating and cooling curve, except the heating and cooling curve is at a single pressure. Whereas the phase diagram allows you to understand how temperature and pressure impact the state of matter of a substance. Okay, folks, that be it. I have no more. Yes,
So,
come on, come on.
just out of curiosity, is there such thing as a supercritical solid?
No.
Okay. So, I mean,